x squared e to the 1 over x. If you take it a second time, unfortunately this time you have to use the not only chain rule here, but also the product rule. So the product rule, right? So if we take the derivative here, let's say here, this is going to be minus 2x to the negative third power times this, and then the derivative of this, so minus makes plus. The derivative of this one is going to be, again, the same process, so minus x to the negative 2x e 1x times another that. Okay. So if we just try to make this a little bit nicer to look at, let's see what we get. So we just have this here. And now, so notice here we have positive, because negative, positive, e to the negative 4 to e to the 1 over x. Right? X squared, my x squared gives you negative 4x, right, when it comes to it. So a little complicated, but hopefully, you guys remember your derivatives essentially there, right, when it comes to it. Okay. So again, if you want, you can make this a little nicer. We could just get rid of the, or not get rid of, but just factor out the e to the 1/4. So this ends up being essentially like that. Okay. Oh, and actually, I almost forgot. Second derivative, this ends up being a positive, so this is a positive. There we go. A little mistake there. Okay. All right, so now that we have the second derivative, how in the world do we find this k value, right? Because that's the most important thing, find that k value, and then we just plug it in and be done with it itself, right? So if we go back to over here, so we know the absolute value of the second derivative, which is equal to exactly what we have here. Okay. Now we got to figure out this k value so that this actually makes true. That's the problem. Now, in order to do so, what we're going to do is manipulate this in a certain way. Okay? So we know that 1 is less than x, right, according to our data, and we'll call it here. Well, what if I flip it around now? So what if, so therefore, 1 over x is now the opposite. So now 1 over x is actually less than 1. Right? So if you're not sure what did I just do, let's do a little example. So we all that's agree, right? 5 is greater than or equal to 3. But now if I swap it, right, if I flip it to a fraction, is it still the same equality? No, right? The inequality actually now changes to that. So that's the same process when it comes to flipping. And we're actually going to be doing this a lot of this semester when it comes to it. So whenever you have a value is less than another value, when you bring it over a value, it actually swaps the inequality. So a good little lesson, right, when it comes to it. Okay. So the reason why we care about this is, well, what if we let 1 over x equaling to 1 in our scenario here, right? Just because we know it has to be a maximum of 1. So we know if it's a maximum of 1, therefore it cannot be higher than a certain value. So if we let 1 over x equal 1 in this whole scenario, notice this just as being a 1, this is a 1, and then 2 plus 1 gives you 3. And also this is a 1. So this is just 3 e to the first power. And that is going to be our k value in this equation. Okay. Again, the most important thing is you guys, once you find your k, is you got to somehow plug in a value into here to make it strictly less than that value. So you want to figure out the maximum, and it's using manipulation usually when it comes to this case or that case to help you out. Okay. All right, so now we have this k value. Now we can just plug it into here. So we know the absolute value of this error for the trapezoidal rule is going to be less than or equal to our k, which is 3e, times the subtraction of b minus a. So in this case, 2 minus 1 is just 1, raised to the third power, all over 12 times n. In this case, n is 10, to the second power. Okay. Or essentially, this is just 3e over there. 3e over 1200. So that's our approximate error if we would do find this area using 10 increments of rectangles. That would be our error itself, which is very, very small. So, which is pretty good, right? We want a small error itself. Okay. Now again, notice the whole work is already done for the next one. So once you find k, that's the whole process, is finding k. Now we can use find the error bound for also the midpoint using the exact same k value, which is the best part. So one's kind of free if you do it that way, because now the error from the midpoint is again less than or equal to that exact same k value. This difference is still 1 raised to the third power, all over 24 times 10 squared. So therefore, our error bound is less than or equal to 3e over 2400. Which again is even smaller, right, when it comes to that portion there. Right? Okay. So what if we wanted a little different type of question itself? So part B is that kind of, so what if we want to go backwards? So in other words, what if they gave you this error and they want you to figure out how many rectangles or how many trapezoids we need in order to keep that error to that accuracy? And that's what part B is all about. It says, how large do we have to choose n so that the approximation is accurate to within 1/1000th? Yeah, 1/1000th of a unit, right? So 0.0001. Now this is what we mean by the error bound, right? So we know that the absolute value of our trapezoidal must be less than or equal to that error. Okay. So therefore, we already know what k is because it's using the same equation. So now I'm going to plug it in and see and just go backwards. So we know, again, going forward, this is going to be 3e over, again, using the trapezoidal, 12n squared is less than or equal to this value here. Okay. And now we just solve for n accordingly. So meaning doing a little bit of algebra, right, when it comes to it. So multiplying and dividing. So essentially, I'll just do a quick little equation to do so. Right? And then dividing over. And then taking the square root of both sides. So let's see how many rectangles we actually need in this case. So it has to be at most n. So if you do this in the calculation, again, take the square root, it gives you 82.42. So it cannot be anything higher than, let's say, 82 itself. So if we do the error bound for our trapezoidal, we'll have at most, or anything that's greater than 82 would be perfectly fine for that error. Okay. So minimum of 82, and again, it can be any higher than that. And then we do the same thing for the midpoint. So notice it's almost identically the same. So the work is the same itself. So essentially all you're doing is now just changing the 12 to the 24. It gives you that. So again, using the same process now. This one now gives us 58.29, so approximately 58 or higher. So that is how many rectangles we need for each to have an error approximation of 0.001 for both the trapezoidal and also the midpoint. So again, right, this is the midpoint error. Okay. All right, so the last type of approximation we're dealing with is something pretty interesting. It's actually you probably may not have seen. It's called Simpson's rule, and it's pretty interesting. Simpson's rule when it comes to it. It's a far interesting one. Something